Good morning, good afternoon, good evening. In this talk, I want to tell you about our success in improving how we can create resource-dependent, embedded, domain-specific languages in a dependently typed language. In this presentation, the language we will be looking at is Idris, a well-known general-purpose functional language with dependent types. But what I'm about to show you is applicable to other similar languages. Let's get started, shall we? What are resource-dependent EDSLs and why should you care? Well, for those not aware, resource-dependent EDSLs are languages that depend on some type-level resource that abstracts over the program. We can use these resources to encode type-level state machines directly into our language's type. On the left, we have the classic example of the door, modeling access to files, handle, sockets, that exemplifies what these languages are and how they are specified. In this example, doors are either open or closed, but they could also be jammed, but we don't look at that here. We can use the language's types to capture this state and associate each expression with a particular state change. For example, pulling on a closed door transitions it from being closed to open. Conversely, we can only shut an open door by pushing it shut. And we can only knock and close doors. Thus, our expressions here denote lawful transitions, lawful interactions, and sequencing of expressions ensure states are propagated correctly throughout the program. What is nice about this approach is that we can support compile-time reasoning about program behavior and also enforce this behavior at runtime. Resource-dependent EDSLs are a great paradigm in which to develop happy little programs. For those interested, there's some nice work by Robert Atke that provides a more formal basis for associating states with computations. We know what resource-dependent EDSLs are, so why should we care? Well, we can apply these languages to many areas. One such area of interest to us is the creation of domain-specific modeling languages. From the creation of global session types, modeling security protocols, and from reasoning about software requirements to physical network structure, we can use these languages to strengthen how we reason about our models and also our programs. These types of languages are great at capturing various domain-specific structural properties, and by embedding these languages within Idris, we can take advantage of the expressive type-level environment to realize our reasoning. With simple type systems, creating such languages is not exactly hard, but it does raise the questions of how we can use these resource-dependent EDSLs to better capture our modeling languages, or programming for that matter, substructural properties, and properties that go beyond the language's structure. This is where effect handlers come into play. Essentially, algebraic effect handlers allow us to separate how programs are specified and reasoned about with how they are realized and how we can deal with a program's side effects. Here, side effects are computations that run alongside our main computation and can impact upon the main program if not handled correctly. For example, dealing with the outside world and with a program's state. With effect handlers, we can separate each effectful aspect of our program into separate properties and merge them together when writing our program. Here, each effect affects the entire program. Handlers allow us to run the same effectful computation specifications in multiple concrete computation effects, thus allowing us to deal with side effects appropriately for each context. Within Idris, the effects library is itself a resource-dependent EDSL and further associates each effect with a specific resource to be reasoned about, the abstract state. So let us look at an illustrative example and see what happens when we use effects to describe a program. Here we present the type signature for an effectful copy function that copies the contents of one file to another. In our type signature, F denotes our effectful context, and we return nothing on success or just an error message. The type level list denotes the set of expected side effects, and note that before we even look at the body of the function, we see something interesting. There are two labeled file effects. This is because in effects, each resource needs to be distinguished. Remember, effects are associated with the whole program. What that means is that within the body of the function, we need to disambiguate between each set of file operations, as I'll show now. The specifics of how this copy function is realized is not that important. The key thing here is there's an issue in building domain-specific effect systems. And this is bad if you want to build programs with multiple same kind effects. And for each same effect instance, we have to disambiguate between them. This also makes it harder to reason about linked effect states. These effects are separate. So how do we address these issues? Well, here is an idea. Rather than associate resources with a whole program effect, why not instead associate resources with variables in our program? We can still have the same separation of specification and realization as we had before, but now bound things have an individual resource that can be manipulated, and we can have many of these same bound things. Now, to realize this, we have to make a few sacrifices. We have to make our list of possible effects explicit in the language design, make it closed, and this restricts compositionality of our programs. Prior work has seen similar sets of boilerplate can be copied across from one language design to another, and this is not optimal. However, by making these sacrifices, we have a more constrained environment in which to do evaluation of programs, but also accumulation of an internal state if that's what we want to do. We can also induce autonomic effect management within the type signature, and as such have no explicit set of effects in the program design. This is the campfire rule. We must clean up after ourselves. And what we really have here is an example of creating domain-specific effect systems. Now, there has been existing published and unpublished work that makes this distinction and allows authors to create expressive, bespoke modeling languages. We've looked at this, we've made something generic, pulled it all together. Let's see what this looks like, or rather, let's get an intuition of what we have made. So here's the doors. A bespoke, resource-dependent EDSL that captures the intuition behind our framework. The type of the doors is parameterized by the type of expressions, whole program state, and how the result of the expression influences this state. Now, the thing here is that our program has to manage multiple states for multiple doors. And our state here is a pairing of a label, a doorknob, and the state of the door. The compiler can distinguish between these labels, and an alternative approach is to replace these labels with the Brown indices. So that's future work. With this setup, we can now describe our expressions in type-level state machines, plural, one for each door. New door creates doors and a type-level resource appending to it the existing set of doors. Tool shows how we can reason about particular doors with the existential quantification, and depending on the outcome of the operation, how to update the context in a safe way. Final expression we show, end, destroys resources, only if the provided predicate holds. In this case is that all doors are closed. And note that we can use the predicate proof itself to safely update our context. Of course, we can sequence expressions together. How could I forget that? But we need to make sure that the future set of states at the type level are correctly updated depending on the result of the expression. This is important. On the previous slide, we have described how doors work, but we also need a way to realize the doors for different computation contexts. To do so, we leverage Idris's interfaces setup, to construct a handler that allows us to associate specific computation contexts with specific ways of realizing the doors. And with this, we need to have an environment that not only keeps track of what real knobs are during execution, but also knows how to determine what a real knob is. We also need to wrap this in a continuation, not just to provide totality, but also to ensure that the type-level states are calculated correctly. Optionally, we have an accumulator to provide internal state, and this is the TY VRED. And note, and just to reiterate with sequencing, our continuation calculates the next step. Further, with this handler interface, we can now provide a monomorphic wrapper functions for a specific context. A pure context with the identity context, and an impure context with an impure context, like IO or IO except. Well, the doors as a bespoke EDSL and our framework resources is the generalization of the doors to allow common functionality to be shared across different implementations. LangM is the core EDSL for binding and context updating, and we have interfaces for mapping abstract types to concrete types. This is RealVar, and for mapping descriptions to concrete computations. This is Handle. Like effects, we still separate specifications from descriptions, and this is what language designers using resources need to provide. We present a singular way to describe a typed, type-level state machine and its type-level embedding in a language's terms, and this is what LangM applies. Much like Idris's effects, we present languages with a single data type, and the abstract types support associating different states to different types. Designers can then realize their handlers for specific computation context and requisite mappings of abstract types to concrete types. However, for language users to construct programs in a clean way, we need to provide some glue to embed the provided terms into LangM and to auto-calculate any predicates used. This is also provided by the language designer, and it forms the language's API. Everything we have is on our GitHub page, but before we ask the final question of how good is this framework, let's revisit our original example, see what it looks like now. So what do we get? At the top, we have most of the motivating example, and at the bottom, we have it rewritten in resources. As you can see, not much has changed aside from a few API differences. Importantly, the labels and type-level list of effects have gone, but we still have the expressive type-level states machines as before. This is great. What about some real examples? So, we've looked at several exemplars. You've seen the doors. We've also looked at domain-specific bigraphs. Bigraphs are a formalism for concurrency by Robin Milner. What we've looked at is how we can create bespoke bigraph instances with bespoke type systems and map them down to a general bigraph representation. We've looked at global value dependent session types with extra properties concerning channel activation. And we've also looked at hardware interface design and hardware orchestration. The last one is special, as it was developed using a prototype version of resources, but we didn't have space to put this in the paper, but you can find it in last year's ECOOP. So what do we find? Well, yes, we can model these in resources, but there are a few caveats. Unfortunately, expressions that update many variables are complex, specifically their type signatures. And with multiple context updates, your type signatures become very noisy. We might need to work on how to develop a better EDSL to describe these type signatures and to make things less noisy. Further, non-trivial handlers are difficult. Projection and value-dependent session types requires environment thinning, and our framework doesn't allow it. But that's okay, because you can create bespoke handlers outside of the framework with a bespoke environment that does the thinning as long as you ensure the states are updated correctly. Unfortunately, handling of properties is lossy. We saw this in our bigraph example. If you don't explicitly pass your substructural properties from your top-level EDSL to the resulting model, it's not passed over. You have to do that explicitly. But that's a design choice you have to make. Finally, we deal with whole happy little programs. We're unable to isolate context as the resources we have are too explicit. We don't really have program compositionality. Separation logic seems like a good approach here. There's some nice work from TU Delft that describes type-level resources using a separation logic-inspired approach. And with that, we should get program compositionality back. And that's it, really. What have we seen today? We have seen a framework that supports creation of resource-dependent EDSLs with a closed effect system. This is great for experimentation, happy little programs, and domain-specific modeling. But the truth be told, effects is better if you have an open-world effect and want horizontal effect composition. But these are two different frameworks for two different scenarios. And the key thing to think about as well is that separation logic is the future. We work with explicit values. This allows for explicit reasoning using predicates. This is great, but it limits program compositionality. And as I said, separation logic might be able to give us this compositionality back. But we need to investigate that approach further. If you want more details about our work, Please do read the paper. Everything is there. I'm going to pause here, and here, and end here. Thank you for watching. If anyone has any comments or thoughts, please ask.